Hi, I'm Jim Garvin, Chief Scientist at NASA's Goddard Space Flight Center, and I want to take you on a journey of the imagination into space, talking about how we bring back the information to space to understand this universe that we live in. And it all starts at Earth. As we study our planet, get to know its vagaries, understand how its climate may react, we are faced with a challenge. Tremendous influx of information, 24/7, day-night information that builds the state variables for our planet. We've been doing this for decades. We're now poised to go into a stage of understanding so that we can predict. And today, our mathematical models that describe our planet are partly data limited. We have some of the boundary conditions, but not all of them. And as we collect more remote sensing data about our planet across the next decade, we will need even more telecommunications bandwidth to paint a picture of how our planet responds. Because Earth is our point of departure. It's where we live. It's how we understand other worlds out there, potentially exoplanets around other suns. So it's our job through an improving, growing space communications infrastructure to bring the data back from Earth. In some cases, terabits a day to understand this planet. The other thing that's very important about the Earth is our planet lives in space. We live in space. And as our planet lives in space, we need to be more situationally aware of what space does to our world. We interact with the sun and we interact with the collisional debris of our solar system. That cosmic collisional debris produces signatures in the climate record of our planet, and yet we are just literally at the precipice of understanding what's out there. Today, we understand what our planet is collided with by pieces of asteroids and comets, but we don't have a good inventory of what they are. And as we embark on a Protect Our Planet initiative, we will need to do a census of those objects with space-based assets that measure them, that see the ones we can't see from our planet, and open our eyes to their possibility. So one of the things we'll need for space communications is higher bandwidth to better communicate with what's happening to our own planet. In addition, as we go to these small objects, we have a mission called OSIRIS-REx that will be visiting the Bennu asteroid, returning samples of it by the early 20s. We will need to interact with these objects. Improved bandwidth of telecommunications will allow more informed interaction, better sampling, better utilization, even redirecting of these objects. These are some of the goals that NASA has, where improved space telecommunications will allow us to do more, better science, better engineering. And then there's Mars, our brotherly planet. Today we've collected a massive information about Mars, but it's incomplete. It's a masterpiece unfinished. We don't have 24/7 situational awareness for this world. We don't have Google Mars for every square city block. Today we know Mars is changing. It's a dramatic world, an incredibly exciting one. We can see in the images we have signs of things on Mars that are actually moving, indicating activity. But we've covered less than 1/10 of 1% at the kind of scales we need to see these motions, to see what might be the eruption of fluids that will tell us where to look under the surface of Mars and how the world works. We also know where we need to go. But today we're limited by just a few places where we have adequate remote sensing to plan missions like the Curiosity rover. This is the Gale crater. After years of work with our Mars Reconnaissance Orbiter producing terabits of data, we now found one of just a handful of places that are well suited for asking questions. Were there any signs of environments where past life could have existed on Mars? Can we get there? In fact, the Curiosity mission launched in late 2011, arriving in 2012, is an example of a high latency robotic solution to exploring Mars. And after a long trip, Curiosity has given us that foothold on Mars, and many of the aspects of that mission, challenging as they were fully autonomous. No interaction, no direct telecommunications, either with assets nearby or with people on Earth. As we move out on this to explore Mars, we'll need to do more. One of the examples of what we've done so well is capture and document what we've done. Here's a descent image, video of landing on Mars from the Curiosity rover. But this data took months to return to Earth. Imagine a telecommunications infrastructure that will allow us to return this descent movie at 4 frames a second, at 20 frames a second within a day or within an hour. We're a long way away from that capability today, and that's the kind of thing we're going to need. And as we look at the rockscapes of Mars and make difficult decisions with Curiosity about where to drill, where to grind up the samples for internal ingesting for analysis with the SAM instrument and the ChemIn instrument, these instruments that tell us analytically how Mars works, we're struck with a big problem. We can only get maybe 1 to 5% of the data we actually collect on Mars back to Earth efficiently. We're bandwidth limited, even with the wonderful telecommunication system we have now. We have to learn to do more if we're going to best use these assets to prepare the way someday for better robots and then, of course, for human beings. We're reminded of the Apollo program, where we went to the moon a long time ago. We learned to do things on the moon that were unimaginable, to drive across the moon. Today we look at the moon from orbiting spacecraft like our Lunar Reconnaissance Orbiter, that with a direct telecommunications link can give us the ability to study the moon up close, almost as if it were Earth. And the Lunar Reconnaissance Orbiter now has returned much of the moon at a scales of 3 or 4 meters across. It's the only world other than Earth we have that resolution. We have Google Moon. As we think about going back to the moon with both robots and people, to look at its exquisite records, we'll need to do more. And the moon is a good test case, a good test particle for how to do that as we choose where to explore with human beings. There's also Mercury, a challenging planet where we've made the first forays with the Messenger mission. Again, a data-starved solution with a brilliant spacecraft mission designed by the Applied Physics Lab that has shown it's a whole new world. Imagine with 100 times the bandwidth what we would be learning about Mercury faster. Sometimes the pace of discovery is driven by the pace of data. And then the planet Venus, an enigma, looking for someone to solve the problems with this world. A world with a gigantic atmosphere, a runaway greenhouse climate state, extreme heat and challenging environments at the surface, a place where to do work there we'll need whole new approaches. The imaging radar missions of the 90s produced a wonderful data set, the Magellan mission, that shows us Venus as it is today, but it's incomplete. It's a masterpiece unfinished. Imagine a telecommunications solution that would take these wonderful radar maps of Venus you see us flying through now and improve the resolution by a factor of 100. Today we see all of Venus at hundreds of meter scale. Imagine seeing much of Venus at meter scale, as if we were there. That's the kind of scale we think we'll need as we study its surface and atmosphere to improve our understanding and ask ourselves, if the Earth were to lose its oceans, how would it evolve to be like a Venus? Our challenges in science are to be predictable and ask what if. And usually those are driven by having the data to produce boundary conditions for models to explain. Today we're also at Saturn with the Cassini mission. We've been back to Jupiter with Galileo. We're going there with Juno. These missions, billions of kilometers from Earth, are incredibly bandwidth limited. Most of the satellites that we send there contain large 12 to 15 to 20 meter radio telecommunications dishes. Most of the power is needed for just communicating at the level of signals that are no stronger than a watt or two to produce wonderful data. Cassini's done that now for almost 9 years. And we can imagine what it would have been able to do had the bandwidth of telecommunications in the Saturn system been as high as they are at Mars or at the moon. So again, what we could do versus what we can do is limited by our telecommunications solutions today, many of which were invented in the 60s and 70s. We're ready for a new era, an adaptable era, so that missions like Cassini, missions to Mars, missions to look beyond into that outer universe can produce the data we need. And then there's the Pluto mission. As we look at the most outer reaches of our solar system and fly by these distant worlds, these dwarf planets, we'll be returning just a smallest amount of information we can possibly collect for a very short dwell time. Imagine if that bandwidth were increased by a factor of 10. We would have so much more information about this whole part of the solar system we barely understand. We didn't even know it really existed other than Pluto just a few decades ago. Our next mission to Mars, the MAVEN mission, which will paint a picture of how the atmosphere works, how it escapes, how it interacts with the sun, the solar wind. Again, this mission is an exquisite science mission, but it will not be carrying a camera, partly because the telecommunications infrastructure we have to get information back from Mars is limiting. It's limiting today. We need to put it beyond a few megabits a second to hundreds of megabits to HD quality as we go to Mars. And then there's the next telescopes we'll send, the James Webb Telescope being our next foray as a time machine into the universe. The Webb Telescope is an engineering marvel being developed at Goddard with partners in Europe, across the country. We will use direct telecommunications from Webb down to ground receiving stations here on Earth at White Sands and elsewhere to allow the information flow to work. But again, we'll be bandwidth limited. The next generation telescopes like Webb and beyond will need more communications to collect more data, to see more of the universe at different temporal, spatial scales, to see more of the stuff we're discovering, the missing matter, the dark energy and dark matter, and even the planets. So our next steps to Mars as well will be critical as we go back to the surface with another kind of roving vehicle in the 2020 timeframe. We will be collecting a whole new gateway data set for the future, which will include, in principle, the containment of samples to eventually be returned by robots and humans. These are bold new steps. So as we look back and look forward, we also look at human spaceflight and the legacy of the space shuttle that carried us so long into space. What will replace the shuttle will be a space launch system with a capsule-based architecture that will carry human beings beyond low Earth orbit. And this Orion SLS system, which will carry us to kinds of destinations we have not been to before, small bodies, perhaps to the moon and Mars. We'll need a space telecommunication architecture that's different from Apollo, more adaptable, higher bandwidth, more connections, more different kinds of interfaces. These will be critical to the future as we imagine humans going to places like Mars. And whether this can happen in the 30s or whenever, human beings to the Mars system, human beings beyond even, will be one of the most challenging things we undertake as engineers and scientists at NASA. And building the telecommunication infrastructure to be aware, to provide the engineering data, the decision-making data, both at the spacecraft, at nearby assets, and on the Earth will be essential. We don't know how we're going to go, but we do know this. Our task is not so much to foresee all the pathways in the future. They are flexible. We will adapt to what we learn about ourselves and the universe, but they're to enable that future. Telecommunications is the great enabler. It's brought the data back for the first 55 years of the space era, and it will be ready to bring back the data for the next 55. So our children's children will have that legacy. It's our job to produce that. NASA's job is to get the ideas to allow that to happen. And so the universe is not going to wait. The more we send to explore it, the more data we'll require, the more new kinds of data. As we learn to measure the unmeasurable, this will require new telecommunications solutions. So today, the answer is, let's communicate, let's navigate. And so that's our job. Thank you.